This is going to be an introduction to type systems. Here we assume that you have studied already the topics of tree-based abstract syntax and also operational semantics, because we very much rely on those. So what is a type system? A type system is essentially a syntax-driven algorithmic means for rejecting programs that would go wrong at runtime. So here's a very simple language that we are going to use for some part of this presentation. The BTL language, basic tuple language. It's a kind of basic language from the Peirce's textbook. So we've got constructs like true, false, zero, suck for successor, prit for predecessor, is zero for test, for zero, and a conditional if, an ifs and else. So here's also an example of an ill-typed term. Something that would go wrong at runtime, because in the condition position we use a zero, whereas we should use something that evaluates to a Boolean value here. So with a type system, we want to be able to reject this kind of term, which is admitted by the syntax, but which doesn't make much sense at runtime. So here's how we actually expect to use a type system effectively. So we hint here at the fact that we might implement a type system eventually, let's say in Haskell functions. And this can be compared to implementing an operational semantics definition as an interpreter. So a type system can be implemented for purpose of type checking. So if we apply the type of function based on some type system rules to the expression suck zero, it would tell us that the type of this expression is not type. So at runtime, presumably this expression would evaluate to a natural number. But if we apply type of to the expression suck true, then it would say this expression has no type, it's not well typed, hinting at the fact that this expression would go wrong at runtime. Actually, our small step operational semantics definition, for example, would get stuck with that term here. So here is the type system for the BTL language. So basically we have one rule per language construct. So it's quite comparable to an operational semantics definition, especially one in the big step style, except that we don't really compute these expressions, but we assign types to expressions. So the first axiom says that true is of type bool type, false is also of type bool type. Second axiom, third axiom, zero is of type not type. And now for suck, we use a premise to establish that the operand of suck must be of type not type, and if so, the compound expression is also of type not type. And the same holds for pret. And for is zero, actually the operand also needs to be of type not type, but the compound expression is 0e is of type bool type. For an if, the expression, the condition position e0 needs to be of type bool type, and the two branches, the then and the else branch, they both need to be of one common type t. This could be not type or bool type. And this common type is then also defining the type of the composed if. So this is the set of rules making up the type system of the BTL language for simple expressions. The rules of a type system can be used for effectively type checking pretty much in the same sense as we used rules of operational semantics definition for let's say executing statements or computing expressions. So the idea is again to apply the rules in a tree-like fashion, where we start with some judgment at the root, and then we just apply a specific rule at each step. And basically the tree has at every level, at every node, has as many branches as there are premises. So for example, here we start with a pret if expression. And so the pret rule has one premise concerned with the operand, and the if rule obviously has three premises concerned with the three sub-expressions, and in this manner we can basically prove or calculate the type of an expression. In fact, if these typing rules meet modest constraints, then it's very straightforward to turn them into a program, as we will see later. We should talk about one important property, the so-called notion of type safety. It's a relationship between semantics and type system, because obviously it doesn't make any sense to define a type system just by itself in the hope it will somehow usefully predict runtime behavior. So type safety is basically the agreement that type system and operational semantics fit together. So usually we make a statement of type safety relative to a small step operational semantics, and type safety breaks down into two sub-properties. First one being called preservation. So preservation means that if we, according to the type system, know that expression E is of type T, and if we, according to the small step operational semantics, can make one step from E to E prime, then the resulting expression E prime must be of the same type T, so preservation. So type safety also requires progress. So progress means if we start from a well-typed expression, I mean expression E of some type T, then either E is in value form, which means we don't even expect to make any further steps, or if it's not in value form, well, then it must be possible to make another step. In other words, the small step semantics doesn't get stuck on well-typed terms E. So if we have more complicated languages, then of course preservation and progress needs to be slightly adjusted, but you get the overall gist. It's about relating type system and semantics in a way that semantics doesn't change the type of a term, and also semantics doesn't get stuck on well-typed terms. And in this manner, we are sure that type system and semantics fit together very well. Okay, now let's look at how we can implement a type system. So here we took the type system rules of BTL and just turned them into straightforward type of function. While on top of this, we also defined a well-typed function, which basically just checks whether an expression has a type or not. And so it returns the maybe type into a bool. Okay, so we have not type, we have bool type. Type of maps an expression to a maybe type, so we return nothing when we claim that the expression is ill-typed. So obviously, just as in the rules of the type system, the type of true is bool type, ditto for false, type of 0 is not type of suck E, well, it's pretty much the type of the operand. Same for pred. And for a 0, again, the type of the operand needs to be not type, but the resulting type is bool type, and so on and so forth. So we just very literally implemented the rules of the type system. Now, let's also look at slightly more interesting programming languages and in that type system. So here we look at imperative programs. So the language in the software language book is called BIPL, Basic Imperative Programming Language. And so we've got typing rules here for all the statement forms. And BIPL is special insofar that we don't declare variables. So effectively what we do in these rules, we sort of infer the types of the variables. Okay, let's start at the top. So given some type assignment, I mean a mapping from variable names to types, M, an assignment is well typed if the right-hand side expression E is of some type T. And if X is not already bound in the type assignment, well, then we update the type assignment so that X now maps to T. And for the case that X already had a type assigned in the type assignment, we have a second rule for assign. We basically say that the type of the right-hand side expression must be the same type as we already had assigned for X in the typing assignment M. Okay, so for a sequential composition of two statements S1 and S2, we say it's well typed if we can show that the statements S1 and S2 are well typed, and we essentially thread the type assignment M0 through S1 and then through S2, and in this manner we compute de facto the type assignment for all the variables in S1 and S2. Well, for if, we check that the type of the condition position E is bool type, and then we just require that we get the same kind of type assignment M2 when starting from the same type assignment M1 for both S1 and S2. And for while, we just assume that the type assignment is not changed by the body of the loop. So we could argue about the specifics of these rules here. We leave this to the discretion of you. Okay, so here's also the second part of the type system for imperative programs. This is about the types of expressions. This is pretty straightforward. So basically an integer constant is of int type, and a variable is of the type that is assigned to the variable in the type assignment. And for unary expressions, well, we determine the type of the operand, and then we use some auxiliary judgment, unary underlined, to check that the operator at hand, for example, negation or logical negation or integer negation, that it fits with the operand type, and we also delegate it to this judgment to compute the resulting type. And the treatment of binary expressions would be exactly the same. Okay, so let's also look at a type system for simple functional programs. So here the assumption is that the functional program consists of many function definitions fs, and there's a main expression e. So what we do is, okay, we take apart the list of function definitions and we check val typeness of each function f1 up to fn. And then we also check that the main expression is of some type t. Okay, so how do we check that function definition is val typed? Well, to this end, we assume this structure here of a function definition. That is, we have a function named x. We have argument types t1 to tn, result type t0. We have the formal argument names x1 to xn, and the body of the function e. And so basically we check that the body of the function e is of the result type t0 in an environment where we have still all the functions fs, because they might be applied within the body. And we also assume this component of the environment here where we bind the argument names to the argument types. So we can show that E is of the expected result type D0, assuming the arguments to be of the declared argument types. Here's the second part. It's dealing with the constant forms of expressions. Int cons, bool cons are of the corresponding int and bool types. And for an argument occurrence in an expression, well, we look up the type of the argument name from the environment. For an if, it's pretty straightforward. Again, we enforce that the condition is of type bool, and the then and the else branch need to be expressions of the same type t, which is also the type of the compound if. And the treatment of unary and binary expressions is pretty much the same as for the expressions in the imperative programs. So the most interesting case is the well-typedness of function applications. So we've got a function application. The name of the function is x. The actual argument expressions are e1 to en. And so we can show that this application is of type T0. Well, if we first determine some types for the actual argument expressions, so this is T1 to Tn, and then we check that indeed there is a function definition in the list of function definitions fs, such that, well, it's the right function name, x, that we apply, and the declared argument types T1, Tn correspond, they are equal to the types that we determine for the actual argument expressions. We don't really care about the names of the arguments here, and also not about the body because we checked this already, but we care about the result type because this is the result type of the function application. So that's it. All the code for this presentation is online, so there are Haskell and Prolog based type checkers for the languages that we discussed, BDL, Bibble, and BFBL. And the software languages book holds a chapter on type systems where it goes into quite a bit more detail. And we will also cover lambda calculus at a later point, which is also an interesting subject with regard to typing. Thank you.